Okay, we are on page 10 of the notes for chapter 3. We are about to introduce what it means to be independent events. Here's the formal mathematical definition. Two events A and B are said to be independent if the probability of event B given that A occurred is the same as the probability of event B. In other words, event B does not care that event A occurred. Okay, so think of it like this. If you were to, let's say B is the event that you flip a coin and it lands on heads. So that's the same here. This is heads. That's event B. A might be the event that it's raining. Spell it. Raining. Outside. Now if it's raining outside, that has zero impact on whether or not your coin lands on heads, right? So the probability of getting heads, given the fact that it's raining outside, well, that's a half. That's the same as just the probability of getting heads. So we would say that raining outside and landing on heads are independent events. They do not have an impact on one another. Now, sometimes it can. So for example, if B was the event, like what's the probability that I'm going to get wet? Well, if it's raining outside, that changes the probability of whether or not you get wet based on whether it's not raining. So, it's possible. We definitely have events that are not independent, that one event affects the probability of another event. But to be independent, the idea is that event B does not care that event A took place. The probability of this, B given A, is the same as the probability of B. Okay. So here they give us, a couple little silly examples. It says we're going to flip a coin twice in successive trials. So event A is that my first flip is heads. Event B is that my second flip is heads. The probability of A getting heads is 1/2. The probability of B flipping a coin and getting heads is 1/2. The probability of B given A, that's the probability of the second flip getting heads, given that the first flip was heads. Well, let's think about that. When you flip the coin the second time, it doesn't matter that the first time was heads. The coin doesn't keep track or no. So this would also be just the probability of getting heads, 1/2. These guys are equal. Mathematically, that says they are independent events. But again, I think we just kind of know that. Let's take a look here. Suppose we roll a die and then we flip a coin. A is going to be the event that we roll a 1. B is the event that our coin shows heads. All right, so remember, when we're rolling a die, our sample space is 1, 2, 3, 4, 5, or 6. That's all the things that we could get out of a coin flip. Okay. So the probability of rolling a 1, well, out of the 6 possibilities, there's only one way to get it, right? There's only one 1 in that list. Now this is a little silly. The probability of getting a 1 on the die, given that your coin flip landed in heads or resulted in heads, well, the die has it doesn't care what the coin is doing, so it's 1/6. They're independent of one another. Okay. The probability of flipping a coin and getting heads, that's event B, that's 1/2. It's going to be the same here. The probability of flipping a coin and getting heads, given that you rolled a die and got a 1, who cares? It's still just 1/2, right? Rolling a die, flipping a coin, those do not have an impact on one another. We say that they are independent events. Here's another little example. So it says, suppose we draw a single card out of a standard deck of 52 cards. Let A be the event that we get a heart, and B be the event that we get a king. So the probability of A getting a heart, well, out of 52 cards, there's 13 hearts, right? So that would be 1 out of 4. The probability of A given B, that would be the probability of A drawing a heart, given that I am holding a king in my hand, right? That I already drew a king. All right. Well, if you think about it, if we drew a king, right? We know we've got a king in our hand. There's only 4 kings in the deck. Okay. So of those 4 kings, what's the probability of getting a heart, right? Well, there's only 1 king of hearts, so it'd be 1 out of 4. So in this case, we would see that these are considered to be independent events, right? Because the probability of one thing has no bearing on the probability of the other. They are independent from one another. If you are finding this, all right, and when you go find the conditional probability and its probability is changed, that means that B is playing some sort of an impact on the likelihood of A occurring. Okay, and so in other words, it means that A is kind of depending on what happens with B. So in this case, though, they're independent because, again, the probability of A alone is the same as the probability of A given that event B happened. B had no impact on the likelihood of A happening. Okay. Let's see this one. This one I think is in the homework, but I'm just going to I'll just go through it real quick. We've got another contingency table. What they've laid out is they're talking about medication and getting the correct dosage versus wrong dosage, and 2 types of labeling on bottles of medicine, whether they're listing just the concentration of the medicine or the ratio of the medication you should be taking. So what do these add up to? There's 13, 25. It looks like there's 28 data values here. So we don't really have to even understand fully what's going on about the labeling in order to do the probability. It's saying what's the probability of someone selecting a correct dose or getting a correct dosage. So when a concentration label is used, you've got 11 people getting a correct dosage, 3 people getting a wrong dosage. When a ratio label is used, you got 2 people getting a correct dosage, 12 people getting a wrong dosage. So the probability of getting a correct dosage, that's everyone in this category. All these guys got a correct dosage. So that probability would be that out of the 28 folks or data values we have, 11 plus 2, or 13 of them, had a correct dosage. So 13 out of 28, or 0.46, would be the probability of someone getting a correct dosage, regardless of the labeling. Well, now what they're doing is they're saying, okay, well, let's restrict this type of labeling to just, let's assume we're looking at ratio labeling. So if I'm looking at ratio labeling, what's the probability that I get a correct dosage, assuming that this is what's taken place? So ratio labeling means, okay, well, I'm only talking about these people now, right? I'm only talking about those folks. It shrinks down my sample space. Now my sample space is only 14 values. The probability then of getting a correct dose out of those 14 would be 2 out of 14, which according to the calculator is 0.142, or 143 if you want to round it. Okay, so it says, are the dosage correctness and label type independent? So is correct dosage independent from the type of label you use? I think the answer is definitely no. They are dependent. Remember, to be independent, we would need this probability and this probability to be the same, but what we have is we have the probability of the correct dosage is not equal to the probability of finding the correct dosage given that we're using the ratio label format. In other words, this had an impact on this probability. Okay, it's not the same as just the probability of getting the correct dosage alone, so they are not independent. They are dependent. Okay. So let's see. Does knowing that we have a ratio label increase or decrease the probability of correctness? It looks like it decreased it, right? Because as a standalone, the probability of just getting a correct dose was 46%. Well, if you say, well, they're using a ratio labeling format, well, my probability of getting it correct went way down. Okay, so this decreased it. Okay, all right. See what we could do on page 11. Actually, I'm going to, this is a good stopping point. I'm going to stop this video because I only have like 4 minutes left, and I'll make a new one starting here with the multiplication rule. Be back.